Hello guys, welcome to my channel Technobuzz. In this video, I will present some post-processing provisions available in OpenFoam 12. Please do like, share and subscribe and do not forget to click the bell icon. So let's start the video. In earlier video, I have shown how to load UNV file in OpenFoam 12. I used lid-driven cavity to show the procedure. The video link is given in the description. In this video, I will continue with the same lid-driven cavity case and explain the post-processing activities. Function objects are OpenFoam utilities or tools which can be used for post-processing activities. During runtime, these function objects can be used to generate additional user-requested data, simplifying the settings and improving processes. In earlier versions, these functions are added in control dict file in system folder. In OpenFoam 12, a separate file with name functions can be added and saved in the folder system. In this video, let us explore some of these post-processing tools which are generally used in most of the CFD simulations. The list of function objects which are available in OpenFoam 12 are listed here. We will explore fields and sampling. These are the generally used function objects where a lot of data is extracted. In this video, let us see how to extract and save the data of velocity components UX, UY and UZ. By default, OpenFoam saves velocity magnitude U. Then we will explore how to save the plots of residuals and how to monitor the plots of residuals dynamically during the runtime. Further, we will see how to extract data for graphs or profile plots. Finally, I will discuss the procedure to extract the data at selected points which are called sensor points in the simulation domain. In HVAC and other industrial floors, sensors are placed at strategic locations to monitor the values of temperature, velocity, scalar concentration, pressure, etc. So we will see how to extract this data from the OpenFoam simulation. Now let us start writing the file functions in system folder. This is the file path. We write the file functions in system folder. You can copy paste any of the existing files and rename it as functions. Then there is a standard block which we add at the beginning, form file, and the object is functions. Then to extract the velocity components, we need to add this block. So this contains type. We write here components. So here these components you can write any name. Then comes libs. So this is the standard library lib.so file which contains the function objects. So we add this here. The field, the state variable, the vector name should be given here. So in this simulation, velocity is a vector, so we just write u. No need to write ux, uy, uz. We just write u so that it will extract the components. Write control, here we give time step. So this will take the time step given in the control dict file. So after every time step, the data of all these components will be calculated. Write interval, here I have given 1000. So this value should be same as that is given in the control dict file. Now let us write the file functions. We need to add the file functions to extract the velocity components. Now let us just copy one of the files here, copy paste it and rename this file as functions. Okay, then open this file. So till this part everything is fine. So the object is functions. Then add location, system. Okay, so object is functions. So this part is fine now. Now we delete this part completely and we need to write the new functions part here. So this is the object class components. The type is, we need to give the type as components here. So this takes care of the velocity. Libs you can use the same and field is u. And the right control here is time step, so it will take from the control dict, and right interval should be 1000 here. The value should be same as the value given in control dict file. So this is the file which we need to add in the system folder. Now let us add the function object for residuals in the file functions. There are two ways of adding residuals. The first method is just add this line in the file. This line saves the residuals which can be loaded in Paraform to check the plots. The second method is dynamic monitoring. If one wants to dynamically monitor the residual plots during the runtime, then we need to add this block. So here residuals is the name. We can add any name here. Then the type is residuals. Again, this is the function object library. Then enable is true. I hope even if this line is not there, it will work. Then the right control, as I told earlier, it should be time step and the right interval is 1000. Now the fields here in the bracket we add u and p. So the residuals of velocity components ux, uy, uz and pressure will be calculated and saved to the residual plot. Once this is done, while the simulation is in progress, open a separate terminal, set the path to the working directory, then type the following command so that we can dynamically monitor the residuals. Now let us add this block in the file. Now come back to the file functions. Now let us add here the block for residuals. So this will extract the residual data and save to the file, which can be loaded in ParaView and checked. For dynamic monitoring, we have to add additional block here. So I add this block here, so residuals. So this is the residuals block. I have explained all these fields earlier. Now let us add the function object for graphs or profile plots. The corresponding function object is graph uniform. The function objects can be added in a single file with the file name functions, or they can be added as separate files. The function object name should be used as the file name. If the function object is added in the file functions, then block is written this way. We have graph, any name can be given here. So the required data is starting point and ending point and number of points in between, and the required fields and the corresponding axis. Now here, this is the cross section of the lid driven cavity. In the x direction, this is the starting point and this is the ending point. So these 2 points are to be given here. Then I select number of points as 30 and the fields are u and p. This is the velocity and pressure. The axis in x direction. Similarly, we can write the graph in y direction. So the starting point is this point and the ending point is this, and the direction is y. If we need to add, or if we want to add this function object as a separate file, then we create a file with file name graph uniform and the corresponding syntax is given here. Now let us write this syntax in file functions. Now in the file functions, let us add the function object for graph in x direction. So starting point, ending point, and other details are explained here. Now at the same time, I would like to add the function object for graph in y direction. So this is it. Now let us add the function object for probes in file functions. The corresponding function object is probes. Let us take a single point in the lid driven cavity domain. This is the midpoint of the domain. So the block for the function objects probes will be something like this. This is again the name which we can give as we need, like probe 1, 2, 3, something like that. Then the type is probes. The function object library is libsampling.so, and here we list out all the points. Currently I have given only 1 point, so we can add more number of points here. The required field is u magnitude, that is velocity. Then again these two are similar. Right control is the time step and the interval is 1000, which is same as the value given in control dict. And this we usually add so that the results will be saved to the post processing folder. Now for OpenFoam 12, this syntax is working well and saves the probe data at every time step. Now let us add this syntax in the function file. So now let us add the function object block for probes. So here it is. So finally we have added function object blocks for plotting residuals to save the residual data at each time step and to monitor residual plots during runtime. Further, we have added function object block for velocity components to save the data of velocity components at each time step. Then we have added function object blocks for profile plots in X and Y directions. So further, we have added function object block to extract the data at specified probe or sensor location. Now let us revisit all the files in the folders 0, constant and system before launching the case. The folder structure of lid-driven cavity is copied from the OpenFoam tutorials and pasted to this working directory. This is the UNV file which is created in Salome. Let us explore the folder structure. Let us go to 0 folder. The case is set up for laminar simulation, so all the files related to the turbulence are deleted from this folder. So you have only two files, U and P. The exporting procedure of a UNV file in OpenFoam 12 is explained in my earlier video. The link is provided in the description. You may explore that video for more clarity. Now in constant folder, you can see polymesh folder. When you open this file boundary, we can see two boundary groups, wall and source. The patch for wall is wall, and we leave the patch for source as patch only. So the case, as I explained, is laminar, so the simulation type is laminar here. This is fine. Now in the system folder, we go to control dict, and this is same as the earlier case. So the simulations will be run up to 100 seconds, and this is a time step. So this is the right interval 1000. For every 1 second, a result will be saved. Okay. Now let us open two terminals and set the path to the working directory. In one of the terminal, let us type the command foam run. Now the case has launched. So once the simulations are launched, we can see a new folder created here, post processing. Within this folder, we see number of folders created for residuals, probes, and graphs. In residuals folder, you can see the data of residuals saved into this file. Similarly, the data for probe is saved in this file. Similarly, the data for graphs are saved within these folders. You can see here, this is a line. And for X, again, this is the data. So now all the data is saved to these folders. Now let us go to the second terminal, and here type the command foam monitor. Post processing residuals 0 and residual data. Now with this command, we can dynamically monitor the residual drop. Now you see here, the drop can be seen. The residual plot can be seen here. As the results are saved, this plot will be updated accordingly. So we can close this. We can close this plot Whenever there is a new result saved, the plot will be updated here. We can also close this window, and when a new result is saved, the plot window will pop up again. If we want to see continuous variation in this plot, we have to increase the result saving interval, but that will slow down the simulation. So finally, the simulation successfully completed 100 seconds. Now let us explore the folder post-processing. So here is the data. Let us open the graphs folder. So in this folder, you can see the profile data is saved at each time step. So we can extract the data at the last time step. Open this file. So this is it. So this is the x direction from 0 to 0.1, and the velocity profile in x, y and z directions are plotted here along with pressure. Now same is the case with graph y. Now let us explore probe. In probe, all the data for each time step is appended to a single file. So we can see here only one folder, 0. So this is it. Here we can see the probe data. So the point is the center point of the lid cavity, and this is the time, and the corresponding values are given here. So this is the data at 100 time step. Fine. Now let us explore residuals. Here too, all the data is appended to the single file. Let us open this file, residuals. So this is the time, first column is time, and here you can see ux, uy and p. Surprisingly here, though the case is a 3D case, we see here only ux and uy. uz is not saved here. So the reason for this is, let us come back to the initial boundary condition file. So here in u, we have specified empty to the boundaries front and back walls. So this is the reason why the solver treated the case as 2D and only x and y directions are solved. If we want to treat the case as a 3D case, then we need to make it as a wall. So let us check this one. Let us copy this no slip and update here, no slip. Okay, then close this file, open this file, P. Now here too, it is 0 gradient. So now we have treated the front back wall as a wall. Now let us delete these 3 files. Come back and go to constant folder, polymesh, and open this boundary file. And here for the front and back wall, make it wall. Save it and come back. So now let us delete these results. And even this post processor. Now all the results are deleted. So open the terminal and set the path to the case directory and just launch the case. Now the case is running. Let us see the post processing folder after some time. So now the case has run for some time. Let us explore the results now. See, 6 results are saved. Now let us open the post-processing residuals and open this file. Now here you can see UJ is saved. Now the case is treated as 3D case, and it is the solver is solving the case in all 3 directions. So fine. This is what we need. Now once the simulations are completed, we can load these data in ParaView and plot the results. Thank you for watching this video. I will make another video in which I will explain the post-processing of this data in ParaView. Please do like, share and subscribe, and do not forget to click the bell icon. Thank you.